Hello, Moses.
Hello. How are you?
Good, good. No one hear it.
All right.
You're the first. I did get your exam. You sent an email. I could
Yes.
get back to it. Yeah.
Okay, cool.
And
did you finish grading the midterms for this class?
oh no. Oh, I forgot about it. Yeah.
You're so disappointed with them. You just
Yeah. But I think I did make up my mind, and I said that okay, I'm just going to grade normal. So I decided that first midterm I'm just going to I feel it is a little not. It's an outlier. I think that's the way you put it. Yeah, but that's okay. I mean, that's like we have more time.
Yeah, the next ones will be in class.
Hopefully, I stopped predicting these things.
Yeah.
Yeah. Hopefully, yeah. It depends. I also change mine. Sometimes I like take home also. It depends on the kind of questions I build.
Yeah.
But at least a few questions will be nice to have in class, I guess. Oh, Luke. Hey, Aliyah, Jordan.
Hello. Without a camera today. Wife's got the computer at school.
Ah, okay. Oh, Khaled. So it's face-to-face in Missouri. So all the students come to school. Is that correct? You mentioned this before.
Yes, but like half our school is quarantined now.
Wow.
Yeah, it's a big mess.
Yeah.
Yeah. So everything was face to face, but
Yeah.
I guess as soon as one kid catches or, tests positive, then everybody that was within like a 2-week period, if they were within 6 feet of that student, they had to quarantine as well. So basically half the school is quarantined. It's a big mess because, they planned on doing everything face to face, and then now they're trying to do online and face to face. So it's for all the quarantine students, they need access to the class. So it's,
True. Oh yeah, that's correct. Yeah, we have been lucky until now here. Let's see. To a certain extent, lucky, I would say.
yeah.
Okay. Oh yeah, now there most of us are here who is not here. Michael. He's usually there. We'll wait a minute. It's already 9:38. Yeah. Oh, there you go. Hello, Michael.
Hi.
Yeah. Now that all of us are here, I have a question. How many of you are taking qualifiers this weekend? No one. That's good. Okay. I'm surprised. Yeah. I expected half the class to be same.
We're all relatively new students.
I guess. Yeah. Okay. Okay. That's fine. So there was a homework due today. If you're not taking the qualifier, let's assume that it is due today. But otherwise, you have this luxury. I don't want to say otherwise. That becomes a this week we will be a little relaxed about the deadlines. That's the way to put it. But to those who don't have the qualifiers, I would suggest that don't use the lenience. I think you'll get behind. So use it to just finish it off. Okay, that's reasonable. Okay.
Yes.
But you can, if you want to. You know, Aliyah is taking qualifiers. So she mentioned. Okay. Anything else anyone wants to comment on the exam? Or sorry, not exam, on anything about the course? I was mentioning a few minutes back to Moses, I haven't graded the exams yet, but I have decided that I'll be grading it normally, like not being picky or anything, just the usual grading, lenient grading, let's say. That's what I can expect, but I have not got to it yet. Like I'm working on I have a big class. I'm almost done with the grading there, and I'll get back to this. So. Yeah, I was asking, do you guys have anything to comment or about the course? Now we have gone pretty good bit, like about few. How many weeks are over? Like I think 5 weeks, right?
Yeah, I think this is the 5th week, right?
This is week number 6.
Oh, is it?
Yeah,
Man,
we've completed 5.
So,
week 6 already.
yeah. Okay, so we had homework 4 due today. So homework 5 I haven't yet posted, but it will be up and by end of or a few hours, let's say. Have the questions. I just have to select the questions. This is 22 plus 7, right? 29. We were working on analytic functions. We defined, we introduced the complex numbers and then defined a class of functions, not all functions, a class of functions that we called it as analytic function on a complex plane. So, analytic function. So these are, in general, if you have a function to be defined on a complex plane, you can think of it as x, depending on x and y. Z here should be thought of as x plus iy, where I is square root of -1. Right. And it is always possible to write it in the form u of x y plus I times b of x. It depends on two variables, two real variables, x and y, and z is complex. You could also think of this as f is equal to f of z comma z star, and maybe I should, so then it's a different function. So f is how do we put it? This is x y first. So, and if I replace x in terms of z and z star, and this is a new function f prime of z and z star, where z is equal to x plus iy, and z star is equal to x minus iy. So that's any function on the complex plane. These are not analytic functions yet. If it's an analytic function, they need to at least satisfy Cauchy-Riemann conditions. The Cauchy conditions. If these functions satisfy these conditions, then they are called analytic functions. In that sense, they are very constrained functions. They're very, it's not the whole, all possible complex functions are not analytic. A small set of them is. And the conditions are du by dx is equal to dv by dy, and d by dx is equal to du by, oops. Like this has a -1 associated with it. So that's a way to remember it. Let me write it down specifically. It's equal to dv by dy, and du by dy is minus dv by dx. A simpler way to see it is that if you're in terms of z and z star, partial derivative with respect to z star of the function f prime is actually equal to 0. That means to say that there is no z star in there. So if you ever see a function that you can write in terms of z star, then it's not an analytic, and it loses a lot of its interesting features. Another way to look at it is that these are very constrained functions, like they're strictly bound. Once you give one point, the second point doesn't have much freedom. The second point is pretty much dependent by the first point, and by that I mean closely knit points. In that sense, as we plotted out yesterday or in the last class, what we did was we defined the derivative on a complex plane. Since there is no z star, we can simply say there is only z there. So, and we defined this to be f of z plus delta z minus f of z divided by delta z. And the way we required or derived the Cauchy-Riemann condition, at least the motivation was that it should not have any dependence on delta z. There should be the first leading term should have a delta z, and that goes away. So derivative of this is independent of how you approach. So it is independent of delta z, which is delta x plus I delta y. If I say that a quantity is independent of a vector, where the vector is from the origin, then you would say that it is isotropic from that point. So for example, what do I mean by that? So if this is a point, that's delta x. This, if I go from this point to this is delta x. If I have a small increment extra, so that's delta x plus a small extra dy, and this will be exactly dy, dx is equal to 0. So there's a lot of independent dz's possible, and it's independent of how you change this to z. I could move from this point to there, this point there, this point to there. Wherever I pick this ratio stays the same. The derivative that we define is same. This is different from the gradient operator that you would define in 2 dimensions. Gradient operator would be dependent on which direction you're going. So that's entirely different operation. Here, if you wanted to talk about derivative, pick a point and pick your favorite point next to it, and the ratio will give you the give you the derivative, provided it's an analytic function. But as I told, not all functions are analytic, so we want to be careful about that. So let's explore this feature a little bit. Let's do some example. And this is called isotropic derivative. So this is called isotropic. So if a complex function is analytic, then its derivative is isotropic in the sense it is independent of where you approach delta z from. So let's have a simple function. So we have f, which is z squared. And let's also have as a contrast, right? Let's have a contrast here. So let's say f is also z star. This is the first example. That's the second example. And since there is a z star there, we immediately know that this is not analytic. It doesn't satisfy the Cauchy-Riemann condition. So this is not analytic. And this is analytic. If it is satisfying the Cauchy-Riemann conditions, the best we can say is that it's a good candidate for an analytic function, but still there could be points, special points, which where it may not be analytic. And sometimes we call it poles, and there are various categorization of those non-analytic points. Let's calculate its derivative. So let's choose. So let's have delta z to be delta x. And that means to say what we are talking about is, so we have a function, and let's also pick a point, let's say at z equal to 0. So we want to find the derivative at exactly z equal to 0, and we would like to approach this point from, so this is z and this is z plus delta z. So this is z and that's z plus delta z. I could have chosen it anywhere, but I chose it along the x-axis. Then derivative would be df1 over dz is limit delta x tends to 0 of z. So this is so this is z plus delta x. Z is x plus iy, remember. So this is square minus z square, and then divide it out by delta x. There is a squared quantity in here which will not contribute in the limit. Z square cancels out when I expand. So it is 2 times z times delta x. So this is equal to 2 times z. And at z equal to 0, that's exactly equal to 0. Maybe I should do this in a few steps. So z square cancels out. So z square plus 2z delta x plus delta x square minus z square divided by delta x. And this is equal to limit delta z tends to 0 of z square cancels out, and I have 2 times z plus delta x, which is 2 times z, which I say is 0. If I were to do this for z star, so again let me at z equal to 0, and let's say delta z is equal to delta x. Similar point here, this function is different, so this is a complex plane, and I approach the z equal to 0 point from the x-axis, and later we'll come from the y-axis and see if they are different or not. And again, we do df2 over dz. So that's limit delta x tends to 0 of, this time it is z plus delta z. Then there's the star plus delta z star, delta x star, or no star, right? This is real if I'm on the x-axis, minus of z star. And this is what delta x. Do exactly the same thing. X tends to 0 of z star cancels out, so but let me explicitly write that z star plus z star delta x, and then there is plus delta x square minus z star. Again, z star cancels out. And this time we have z plus z star, which is actually in the limit delta x tends to 0. One more step. Z plus z star plus delta x. In the limit delta x tends to 0, that's just z plus z star, and z plus z star is just 2 times x. But we are choosing it to be exactly at that point. So if at x equal to 0, it is 0. And let's keep it open so that if it comes out to be the same, then at least we can go to other points. Also, since I showed you the details here, maybe I can do the next point slightly more quickly. So this is delta y. So this was the first variation, and now I start from here and make the change from here. So z and z plus delta z is now delta z now, let's say, is y. So again, z is equal to 0, or probably going to come at z equal to 0, but that's independent of this point at this point. Delta z is delta y. So that's a change now. So instead of delta x, this becomes delta y. Otherwise, everything else stays the sorry, delta y becomes I times delta y. Right? So let me do that again. Let me erase this if you don't mind. So that's some more room. So delta z is equal to 0 plus I delta y. Right? There is this I there, so in that sense it's slightly different. The f1 over dz is limit delta z tends to 0, which has I times delta y, and this is z plus I delta y is square minus z square divided by, this time it is I times delta y. That's fine. Again, you do the same thing. Z square cancels out. 2 times z times I delta y. That exactly cancels out. And what we have is, again, 2 times z. Which, if I were to set z equal to 0, is equal to 0. In fact, this will be true for any z, right? At least these two different independent directions in which you're coming in. Okay, so same thing we want to do in here, and for that I will write this answer to be 2 times x, which when I set z equal to 0, this is 0. And get some room. So this time delta z is equal to I times delta y. Limit delta z, which is basically I times delta y, that's going to 0. Z plus I delta y. But notice now we have to take a star. So this is z star. Well, let me put it the correct way. So this is z plus I delta y star. Right? That makes it unambiguous where that minus sign is going to come from. When I make this conjugate, z becomes z star, and also this I changes sign. That's minus z star divided by I times delta y. That's equal to delta z tends to 0. There is z star, and now there is a plus I delta y. There's a minus I delta y. So it is plus I delta y times z star. So this is z star, and there's minus z. And is that clear how it is, how the changes are happening? So this star enters in here, and then I'm just expanding it, and it can be written in this form. Correct me if I'm making any errors in here. So let me check. So this is z star times I delta y, z star times I delta y, and this is minus I delta y times z minus I delta y times z. Z star again cancels out, and in the limit delta y tends to 0, this is z star minus z. So the real part actually cancels out, and what is left out is 2 times I times y.
You said in the limit as delta y goes to 0?
Yes, I did not want to say delta y. Actually, it is delta y, right? It doesn't matter what I is. Yes, so I say delta z, but delta z is I times delta y. So delta y tends to 0. So I'm coming from the top, on the top axis. I'm taking the limit in this direction. That's what it means. The two ways, or not just two ways, there are infinite ways of approaching the origin. I picked two directions out of this. And this is equal to, what did I say? Iy, so this is 2 times I times 1. And of course, one can argue that at y equal to 0, if you were approaching exactly at, if you were taking z equal to 0, then of course the answer is indeed 0, but they're not the same everywhere. Right? If I were slightly away from that point, I won't get the same answer. So that's the feature that this is actually not an, or if it does not satisfy Cauchy-Riemann condition, which is to say that it has a z star dependence in a very simple, naive manner, then they don't give you the same point, except in this case, there is a special feature that z equal to 0 is analytic in a sense. It is analytic at one point, probably. This function is analytic probably at one point, even though like at that point, it satisfies the Cauchy-Riemann condition. Cauchy-Riemann condition has to be checked for at every point on the complex plane. But at this point, it satisfies probably, but it will fail at every other point, as we can see just by taking some very close point to the origin. 1 is to x and 1 is to y, so it will give you different numbers. Okay, so that's a feature of isotropic. We studied some differential geometry in the first few weeks, and we are going to see that this u and v that we have introduced here actually have those features of how can I put this, of surfaces, a family of surfaces. And in the sense that if I get u, v is actually constrained. So let's see what I mean there. Let me change the code. So let me begin by saying that yeah, let's have a function, an arbitrary function of real variables, which has a form a x squared plus b y squared, not x squared, let's say just plus c z. So that's your function. And xy, oh, that is it, xy, there's a z there, so I don't like that. So let me change that. So a1 x1 plus a2 x2 plus a3 x3, right, where x1, x2, and x3 are real. And I don't say anything about a1, a2, a3. ai could be real or complex. If we think of this as vectors, what this means is that we have f of a dotted with x. That's what it means. Let's take the gradient of this. So now we are in 3-dimensional space, let's say. And let's have a gradient operator. This is, in general, gradient could be in any coordinates, but if you're in rectangular coordinates, this is d by dx1 plus j hat d by dx2 plus k hat d by dx3. That's just for inside, I don't really need that representation. Let's me ask, what is a gradient of this function f? And this will be whatever is this argument multiplied by the derivative of that argument, right? So let me have the derivative of that argument written as f prime. Like this means that take the derivative with respect to the argument of the function f, and then I have to have a chain rule in here. The gradient of the way maybe explicitly put that is I have d by dr of a dotted with x, and then d by a dotted with x of the function. But this is the argument itself, so I'll call this, I'll use the notation f prime, so derivative with the argument with respect to argument of the function. So this becomes gradient of, let me change the order here, x dotted with a and f prime. We know that gradient operator acting on a vector in an tensor product manner. So this is a dyadic. This is a dyadic 1. Dotted with 1 is A itself. So this is 1 dotted with A is equal to A itself. So this is the vector A multiplied by prime. Let me operate another gradient of this. So this will become the Laplacian, right? Laplacian of the function f would be gradient of a gradient. Right. But I already found the gradient of f. That's this. This is equal to gradient dotted with a f prime, right? And f prime is I introduced the argument here. It is a dotted with x. So let me do that in the next step. This does not depend on x, so I can move that out. I'm changing orders here. This is f prime. And since this has a dependence of a dotted with x, I can again use the chain here, right? So this is gradient of a function. I again have to do the same operation. I know that I'll get this. So this will be equal to, using this feature, a dotted with a times f double prime. That's a very generic relation, right? I don't need any form for this function f. If in 3 dimensions, if there is a dependence of this function on this kind, then I will have this to be equal to this. And the Laplacian, we could ask, let's ask the question as to what are the solutions for del square f is equal to 0? Like when is the Laplacian of a particular function equal to 0? And clearly, there is one solution one can immediately say. This implies, if you want, either this is 0 or f prime is 0, right? So this implies that either a square is equal to 0, we write it as a dotted with a, or f double prime is equal to 0, or both could be 0. So if you want to satisfy the Laplacian, one way is that construct your A1, A2, A3 in such a way that it satisfies A dotted with A is equal to 0. Correct? That gives us a simple idea how to satisfy Laplacian. And there was in one of the discussion in previous classes, spherical harmonics had shown up. And this is how you begin spherical harmonics, by the way. So you will say that I'm interested in constructing all functions of this kind in 3 dimensions, which satisfy this Laplacian. And spherical harmonics is a way to classify them. So that I won't go further than that. I'll just stop here. But we are doing complex. We are on a 2-dimensional complex plane. Right? So let's see what we are up to. So we have a function f, which is of the kind x plus I y. That's what our function is. We are in 2 dimensions. And this actually does not depend on the dimensions, right? I could have done in 2 dimensions, 3 dimensions, 4 dimensions. So I would have gone through and I could have got a dotted with a in that particular dimension, which is 0. So let's say this is equal, what did I write? This is f of z. So what I meant was, so f of z, which is the same as f of x plus iy. And I want to write it in that form. So I say this is the same as f of a dotted with x, except now my x is equal to x comma y. That's the same thing, x1 to x2. And my a is 1 and I. That's perfectly valid. So I can think of it as vectors now, but A is complex. But then here I did not say require this to be real. Right? So that's there. And then let me ask, when does this satisfy the Laplacian? Now my Laplacian is in 2 dimensions. So this is I hat, this is I hat, not be confused.
What did you say A is equal to again?
A is equal to 1 plus, so if you're in vectors, so this is A, this is equal to x in the x hat direction plus y in the y hat direction, right? Okay, and A is equal to 1 in the x hat direction plus I in the y hat direction. Not a normal vector, right? There's complex elements of the vector. But I allowed that, right? I allowed it to be complex here. A1, A2, A3 could be complex. Right? So that's what this is. Does that answer? Not very easy to visualize because in 2 dimensions we usually don't put in. When we are talking about 2-dimensional vector space, we don't allow, or typically we don't allow complex numbers, but that's what it is. So that's a vector I'm talking. Okay. Helps?
Yep.
Probably
Yeah. I mean,
does.
I still don't, I'm struggling like seeing it, but I'm,
Yeah, insight wise, I agree because 2 dimensional, we are so much used to that, so it doesn't help much. But if you go by this, like have the insight here that if you have a linear combination of x, y, and z, or x1, x2, and x3 with any coefficients, complex coefficients, then a way of a methodology to have Laplacian satisfied is to have A1 dotted with A1 0, which means to say that this is a compact way of saying A1 square plus A2 square plus A3 square is equal to 0. Forget the vectors, right? It's A1 square plus A2 square plus A3 square is equal to 0. That's all you want. Right? And if you're real, then you're stuck, right? If you say A1, A2, and A3 are real, then all three has to be, these are three positive numbers. And there's only one point that that satisfies it. But the moment you allow this to be complex, a lot more solutions possible.
okay. Well, that helps a lot. Just thinking about it like that because, yeah.
So that's what I'm trying to catch on to. If this is real, you're stuck at one point.
Then only if A1, A2, and A3 are equal to 0.
All three 0. But if it is complex, there is a whole whole domain there. And that's what I'm asking again. Now in 2 dimensions, if I say that del, so let me write del first. So x hat d by dx plus y hat d by dy, or in 2 dimensions, the gradient, right? If you don't want the vectors. And then again ask, under what condition is this a kind of function satisfying the Laplacian? Right? And the condition would be the same here, right? This or that, but I'm interested in the first piece. And I would say a squared is 0, so which is 1 square plus I square. If that is equal to 0, then this satisfies the Laplacian, and it is, right? I squared is -1, so this is indeed satisfied. Okay. So an analytic function, so the conclusion is that an analytic function satisfies the Laplacian, the 2-dimensional Laplacian. We'll say more. And again, since I mentioned spherical harmonics again, because you guys mentioned it earlier, this is exactly how spherical harmonics combine. In spherical harmonics, you go into the complex plane. You want A1, A2, and A3. You look for, so the question asked is, give me all possible A1, A2, and A3, right? Which actually satisfies and every possibility. And that classification comes out to be the spherical harmonics, and the angular momentum plays the role there of the classification. So it's kind of a beautiful thing there. Oh, actually, yeah, we have extra credit, right? So look it up in the following way. So this is extra credit, right? So this was, in this manner, this was done by Kelvin, Lord Kelvin. His name was Thomson, actually, but I think they changed their names. I don't know how it works there. So they're also called, yeah, what's the connection between spherical harmonics? You might have to search a little, it's not very popularly available. Spherical harmonics, and I think they're called, or Kelvin's derivation of spherical harmonics. And it's good to say that the website of the course has this SPH, ICS. It's built out of spherical harmonics, like SPH and ICS, the first three letters of spherical and last three letters of harmonics. So yeah, look up and it might give some insight. If you're not able to find it, there was this classic written in 1850s or 1840s probably, way back, right? 200, 180 years back, 1840. There was a book written by three leading, at that time we don't call it physicists, right? Probably philosophers or mathematicians. I think, what's the name? There are three T's. Look for three T's. I think it's three T's. That is where the topology came up. There, the point was that everything, at that time, there was a big deal about all the atoms are decided by the topology of, so there is some string-like structure and how many knots they form decide the topology out there. And that was I think that was the motivation to study these things. Okay, but that's just an extra credit. Somewhere else we'll come across this. Hopefully we can do spherical harmonics in this course. Let's, yes, please.
Yes, I have a question about I square plus I square equals 0. Can you please explain this one?
It is this one here.
Mm-hmm. Yes.
This is 1 square.
One. Okay. I thought it's.
So this is A1 plus A2, right? So we want A1 square plus A2 square.
Mm-hmm.
A1 is 1.
Mm-hmm.
1 square plus A2 is I square, and I square is minus 1. 1 square is 1, so that is 0. So this is immediately suggesting that the analytic function will satisfy the Laplacian. So what do we mean by that? So what kind of equation is this? So let me explicitly do this. So let's say the function f is equal to u of xy, instead of writing it in this form, plus I times v of xy. So what do I mean by the gradient in here? So this is just du by dx plus dv by dy. So gradient here of
Do we want to use the chain rule here too?
Yes, actually, yes. I want to do that. But let me delay that. Let me actually give you more information that. So instead of saying f, let me show that. Yeah. So let me start with u is a function of xy, correct? So I don't actually need f. F is more than what I want. F has two functions in it, right? Two two-dimensional functions in it. So this is kind of a potential, right? In 2 dimensions, you will have a potential like temperature at every point on a plane, right? That's something like that. So this is a scalar function, and then I can define what is a gradient of u, which will be x hat du by x plus y hat du by dy. And the Laplacian would be L square of u would be equal to I take the derivative again, right? Isn't that what I do? The divergence will be e square u by dx square plus e square let me just write this in this. And similarly, I'll have del square of v is equal to d by dx square plus d by dy square of v. But what is this equal to, right? Does it satisfy the Laplacian or not? And for that, actually, I was thinking that I can take a shortcut, but I think we have to go with Moses' recommendation that we have to take the partial derivative, right? So let's do that. I think I'm going in a roundabout way. That is an easier way of showing this, but let me attempt that. Okay. Give me a second. What's the time, by the way? Here the time shows 10:30. Is it correct?
I have 10:32.
Oh yeah, this is not the one that starts at 11. Yeah, okay, yeah. So we have 20 minutes left. Okay, so yeah, give me a second. Let me see if I see the direct path. Yeah, so I think this is a trick, I suppose. I wouldn't have gone that way. So, so to see this, how it works, let's have u of x, y. It's pretty much what I think Moses was suggesting, that we have to use a chain rule. Probably he was saying that we have to take a derivative with z star. If I want to write this in terms of x and iy, I can always write this as a function of okay?
Z and Z star?
Yeah, that's what I'm saying. Is it correct? So is this clear? I'm confused a little. Plus, let's say f1 and f2 of x minus of iy. That's z and z star. Is that obvious as to why that should be correct?
Not to me directly, no.
Yeah, it's not for me either at this point, but in my notes, I say that permits. Oh, I think that's, yeah, this is not the way to see it. Yeah, okay, sorry. Sorry, yeah, okay. I think I know what I'm talking about in my notes. Okay, so let's let d squared plus dy squared of u be equal to 0. Right? And let me ask, under what conditions does this is this satisfied? Okay. So notice that this is not 0 as such. So under what conditions is the Laplacian of u is equal to 0? That's a question we can ask. Reasonable?
It would help if U was analytic.
No, this is u is this real part. It's built out of x and y, right?
Okay.
So, and we are not assumed that it is analytic. This is at this point any random real part of a complex function, right? So this is so u is real part of f of z comma z star. Right? Any part of any function, and we would like to. I think I'm going to show that when the Cauchy-Riemann conditions are satisfied, then this will be true. And then we know that, oh, that's a condition for the analytic function.
Under what conditions is the Laplacian of what equal to 0? I can't tell. Is that A?
Oh, this is u, the same u here.
Oh, okay.
Right? So I was saying, let this be a quantity, and we are, so this is del square, right? Del square u. Let this be equal to del square u, and under what conditions is del square u is equal to 0? Where u is the same, any complex function can be written as a real part and an imaginary part. So this is a real part of an arbitrary complex function, not an analytic function. But we'll show that if this is true, then it satisfies the conditions for analyticity. Okay, so that's what I think I'm going to show. But here I'll use some physics. I think that's fine. If this was equal to 0, if this is equal to 0, that's the same as this is a u is equal to minus of del square over del y square times u, right? And minus 1 is nothing but 1 over I square, right? And does this equation ring a bell in physics?
Yes.
And what is that equation?
The Laplacian.
No, yeah, Laplacian. But in 2 dimensions, there is we have this also, right? X squared f is equal to 1 over v squared. Does this ring a bell?
Yeah, we did that all last semester.
All last semester. And what is that?
I mean, is it not what I just said it was? The Laplacian?
No, something more familiar? No? Stare at it?
Is it the wave function, Doctor?
Yes, it's the wave equation, right? Where v is the velocity. Right? This is the time, this is the x, this is a wave equation, right? This is what governs a wave, any wave. It doesn't have to be an electromagnetic wave, an ocean wave, think of a wave, a vibration at a position and in time. Like a wave is different from oscillations in the sense that there are oscillations in time and position. And then you ask, what are the solutions for this? You have two kinds of solutions. Either it could be forward-going waves or backward-going wave. Again, it's the same. I mean, as Jordan kept saying, this is the Laplacian, right? It's just that this is phi, right? So again, notice 1 plus v, right? You would say distance over time. So the speed is nothing but a way of writing the Laplacian. If you want, if v square is equal to 1 is satisfied, or plus or minus 1, or what is it, 1 plus v square is equal to 0 is satisfied, then you're good, right? That's your condition. Any function that satisfies that is a wave. That's why you have all kinds of waves in the ocean, right? They don't just have sine and cosine, but any function of that kind is a solution. And typically, you have linear combination of two. If you have two such solutions, then linear combination of that is also as a solution. And in that sense, now you say that now it's clear why I wrote that earlier. So since there are two possibilities, plus or minus, you say this is a linear combination. So this is f of x plus iy. Velocity here is in a sense I, and another function f2 of x minus iy. Now, yeah, so now let's see under what conditions. So let's write del Q square, right? So I think I'm just going to evaluate this whole thing, I suppose. Let's do du by dx is equal to df1 over dx plus df2 over dx. Why am I struggling? There's something you're missing. Hold on. Okay. Du by dy is equal to, that's a y there. First, I take the derivative with respect to x, and then I have an I, right? So it is I times df1 by dx. Take the argument and then take the derivative of the argument with respect to y, so that you see the I there. And this one is minus I times df2 by dx. Take the derivative again.
Do you mean the derivative partial with respect to y?
No, this time it is x, right? So what I meant here was that, okay, so d by dy of f1 of x plus iy is the same as do the chain rule, right? This is x plus iy with respect to y, and d by dx plus iy of f of x plus iy. Right?
Mm-hmm.
This is I, and this is the derivative with respect to the argument. Derivative with respect to the argument is either the derivative with respect to the x, or it is the derivative with respect to the iy, right? Either one of them will help you with that. So this is equal to I times same. It's the same as d by dx of f of x, right? Because x doesn't have any coefficient.
Mm-hmm.
X had a coefficient, then there would have been I wouldn't have been able to do it. So that's just that.
Okay.
So that's what I use that in here. Right? And such a simple relation, I'm not able to proceed. Okay. So, but I'm stuck. I have no vision of how to get the answer. Okay. So, but let me try. Okay. So let me bluntly do this, right? So two derivatives. Can we do second derivative of u with respect to x squared? Right. So do this again. So this will be second derivative, right? So I'll get inside. So this is d by d square by dx square of f1 plus d square by dx square of f2, right? That's the same, but let's now see what is d square by dy of u. So y can enter this x, so this is I times d by dx of the f1 over dy plus or minus I d by dx of df2 by dy. But I know how to do derivative of f1 with y, the same trick that I just elaborated on. With respect to y is the same as with respect to x, but putting in an I there. So this is I squared of second derivative of x squared of f1, and this one brings in a minus I squared. I squared is a minus 1, so this is minus of 1 plus. But I just went in a cycle, right? So this is obviously satisfied, which is what I started with. Okay, let me stop here. I'll do this next time in a much simpler way. This is just a two-step problem. To show that this actually satisfies the Laplacian. Yeah.
I think you have to start with the Cauchy-Riemann equations, right?
Yeah, probably. I would think so. But why did I not start with that? Yeah, you want to try that now? Okay, so you're okay. Let me. Okay, so Cauchy. Yeah, I think that that's probably correct. So du by dx is equal to dv by dy, and du by dy is equal to minus dv by dx. Right. Yeah, I think that's immediate, right? Yeah, actually that's what I think you're trying to say. Okay, so take the second derivative. Yes. Of u, this is equal to d by dx, d by dy of v, right? Start from here, take d square by dy square of v, that's equal to minus d by dy by dx. Okay, that's what it is. Now add these two equations. Is that the point, Luke? I think it's a distinct, yeah, thank you. So this is much, oh, what did I do? So this was u actually. So this is u. These two cancel out because partial derivatives commute. That's equal to 0. Okay, great, fantastic. Yeah, I knew it was just 2 steps, I mean, less than 2 steps. So same thing, you can start with v instead of starting with x, start it on the other side, and also you can show
So do these have to be continuous?
yeah, more than, okay, it is, so it has to satisfy this replacement. Partial derivatives should be replaceable, right? So there's a, I mean, typically it has come to be known as well-behaved functions. That's what it's a jargon there, well-behaved function, which means to say that you can actually replace these derivatives as you want. You can think of it as they shouldn't have kinks, right? They shouldn't have this think of a function of this kind. So this is also a function, right? This will be f is magnitude of x. This is one-dimensional real function, right? Its derivative from the left and the right is different, and now you want to extend this to 2 dimensions, right? And you're saying that its partial derivative from the x and y does not match. And actually, I gave an example or an extra credit, right, to figure out a function that satisfies that. And many of you gave examples. I'm not able to come up with one. We will do actually, analytic functions are examples of this kind of function. Like analytic functions satisfy this. So if it is not analytic, most probably it does not satisfy that. And in your homework, you will have this problem to do. Find a function, or I will give you a function that satisfies Riemann, a Cauchy-Riemann condition, and ask you to find out that, oh, actually this doesn't satisfy this property, that in 2 directions it doesn't work out. But yeah, before I deviate from this completely, I was trying to show that under what conditions u and v actually satisfy the Laplacian, and it turns out to be the Riemann, Cauchy-Riemann conditions. And thank you, Luke. So you will see through that helps. Yeah.
So does that mean that in order for f to be analytic, its components u and v also need to be analytic?
That's correct. Oh no, not analytic, right?
They just satisfy the Cauchy-Riemann conditions.
Exactly.
Yeah. Okay.
Yeah. F is analytic. U and V has to satisfy these conditions. In fact, they are so much constrained that I will do this in the next class. That if you're given U, V is determined automatically. Like you don't have any choice for V, except for a constant here and there. You can move things around. So these are so constrained that give me the real value, imaginary value, you don't have a choice. And where do you see that in physics? So there will be, in physics, we will see that if you're doing electrostatics in 2 dimensions, usually we have electrostatics in 3 dimensions. If we are doing electrostatics in 2 dimensions, this will be the electric potential and this will be the electric field. Or, so there's no which one should be which. You can take this to be the electric field, that's the electric potential. And either way, it works for conducting fields. And we will see the analogy there. That will be a nice thing we will explore in the next week. So that's one thing I wanted to. And the second is, of course, complex integrals, which is very useful or which is used a lot in physics. That's something that I'll introduce. And that I think is pretty, once we do Cauchy's theorem, it will come out very neatly out of it. It will be an application of Cauchy's theorem. But yeah, this was good. Thank you. You? That's, yeah.
Luke was our Batman today. He saved Gotham.
Yeah, sick. Yeah.
I just saved my notebook from my old complex analysis course, so
Well, that's not, I mean, I cannot give that excuse. I have my notes in front of me and I'm staring at it. And I know it is 2 steps, but I'm not 2. I think I got lost some, anyway, no, it's like, I was trying to do something in that spirit, starting with F.
Were you a double major in math and physics, or did you just take complex analysis because you wanted to take the course?
kind of both. I was thinking about like getting a math minor, but just a lot of physics majors took like that math course. So.
Oh, okay, gotcha. Yeah, that'd have been nice if my university would have done that. We didn't do that because if you got a degree in physics, you just had to declare a minor in math because I guess you took enough courses that it worked. But yeah, we didn't have to take complex analysis. Although the university I went to is more of an engineering school, I guess you could say. So a lot of the courses are focused towards that.
It also depends on whom you take the complex analysis with. Like if you take it in the math department, often the stress is on the geometry of this, geometric features of that. And when you take physics, you get to see the application side in the sense that how the integrals are used and what I'm going to talk about, like the electrostatic connection of this, which are called conjugate functions.
Yeah, in my math physics course, we didn't touch anything with this stuff at all.
It's not expected, but if you have a bigger department, then there is a good chance that there will be a complex analysis course offered in the physics department itself, and that's probably more useful. But this is good to know. Yeah. Thanks.
Thank you.
Yeah.
Good luck on your exam, Malia, or your exams.
Yeah.
Alia, are you taking the qualifiers?
You talking to me?
Yes.
Yeah. Yeah.
Okay. Very good. Yeah, well, good luck.
Thank you. Thank you. Bye.
Bye.
All right, see ya.
Okay.
Bye, guys.
Enjoy, guys.
You too.